the average value of a function. The average value is the average output of a function. And we know that geometrically, the output represents the distance between the curve and the x-axis. So think of them as the heights. So we're going to try to figure out, on average, what is the height above or below the x-axis along some interval. So visually, let's say I have some function, f of x, and we're looking along the interval from a to b. To find the average height, what we may do is select a certain amount of values between a and b and determine their outputs, which I'm representing by these red lines. We may add together those outputs and then divide by the number of outputs that we chose. That's how we would average that value. So let's put that into a formula. So to get the estimate, what we're going to do is for some constant c, where c is on the interval from a to b. So we're just picking random points from a to b. And what we're going to do is we're going to add up the outputs at various c values, which I'll distinguish by putting subscripts to them. And this is going to continue on to say f of c sub j. And j is going to be an element of the set that ranges from 1, and it goes up to n, where n is going to be the number of outputs we choose to use for our estimate. So we add them all up and then divide by the number of points chosen. So we add everything up, then divide. So to condense that, we introduced summation notation with the Riemann sums. So instead of expressing f of c sub 1 plus f of c sub 2, because we don't know how many we're going to use, we can condense that down into sigma. And j is going to start at 1. So remember, that's our beginning point for the subscript. And it's going to range all the way up to n for the outputs. So this notation says add up all the outputs. But then we want to divide that by the number of points we choose to make our estimate. Now, this is going to give us a rough estimate, and the more outputs we choose, the better the estimate is going to be. Much like our rectangular approximation methods, the more rectangles we used, the closer and closer to the actual area it got. So as we took the limit as n approached infinity, we got the exact area, and that's where our definition for the definite integral came from. So we're going to reformat this thing, and we're going to see some similarities between what we have written here in a Riemann sum. Let's say that the points we choose, we want them to be equally spaced. We don't want to just choose all of our values, say, closer to A and leave all these points that are closer to B out of the picture. So it'd be best, for the best estimate, we would want our points to be equally spaced. And to do that, we take the length of the interval and we divide by the number we want. We take the length of the interval and divide by the number we want. That's going to get our difference in x to get these things equally spaced. And this is the exact same thing we did with our rectangular approximation methods. Now, what we're going to do is manipulate this thing a little bit by dividing both sides by b minus a. And we're going to see that 1 over n is equal to delta x over b minus a. So this is coming from the fact that we want our points that we're selecting for our estimate to be equally spaced to get the best possible estimate. Now, you'll notice that in my summation notation here, this formula that expresses the estimate It's dividing by n, which is the same thing as multiplying by 1 over n. But now we have a representation for 1 over n when I want these points to be equally spaced. So I can rewrite this to be delta x b minus a times the sum of the outputs. So again, why is it multiplying? Well, dividing by n is the same thing as multiplying by 1 over n. So instead of dividing by n, we could have expressed our estimate formula in the following way. Now, here's the thing. When we sum things together and we're multiplying by this value that represents the distance between the outputs, we can manipulate this a little bit further, because when we add things together, say we're doing 1 plus 2 plus 3 plus 4, and at the end we multiply it by, say, 2, well, we could multiply each individually by 2 and then add them all up. That still works. So that delta x, we're going to put it in that sigma summation notation. So we're going to put that inside here. And you'll notice that this reveals something that should look familiar. What we have here is the definition of our Riemann sum. We're adding the outputs, delta x, our base, so height and base, area of rectangles, and we're summing them from 1 to n, where n represents the number of points we're choosing or the number of rectangles when we're looking at it like this. So this is going to be our Riemann sum, specifically our right Riemann sum, because it's starting at 1 and then going to n. And we know when we take the limit of the Riemann sum as n approaches infinity, that's going to be the integral from a to b of f of x dx. So we can replace what I have boxed off in green with an integral, because what I have boxed off in green is a Riemann sum, and to get the best possible estimate for the average value anyway, we would want to take the limit as the number of points I choose approaches infinity. So this is going to become one over b minus a, and we're replacing the Riemann sum with the integral from a to b of f of x dx to reveal the average value formula for a function from a to b. So we want to box this thing off. This is how we calculate average value. And the way we did that was we took the approach of saying, how would I estimate the average value? Because there's an infinite number of points I could select from a to b. So we select some number, add them all up, and divide by the number we chose. That revealed this formula here. We then said, well, it would be best if these points that we chose were equally spaced, calculated here. We manipulated the formula and rewrote our summation that was originally boxed off in purple to get this. Then, using summation notation and the idea behind adding things up and multiplying by a constant at the end, we can multiply each value by that constant and then add them all up, allowed us to input delta x within the sigma notation, and that revealed the definition of a Riemann sum. And then we said to get the actual estimate, what we would want to do is take the limit as the number of points we choose approaches infinity. And we know the limit as n approaches infinity of the Riemann sum is an integral. It is the definite integral along the interval from a to b. So we can make the replacement for our Riemann sum by using a definite integral, and thus we have derived the formula for average value of a function. So to compute the average value of a function from a to b, you are going to integrate that function along the interval and then divide by the length of the interval. So that's what that piece out front is telling you. So calculate the area and then divide by the length of the interval. And that should make sense. If the area is computed by adding up a bunch of rectangles, and we know rectangles are base times height. This is an exact, but it gives you a rough idea. And then we're dividing by the length of the interval, which is the base. All that's left is the height. So we're calculating the average height through that formula. Now, what we can build off of that is the mean value theorem for definite integrals. The mean value theorem for definite integrals says that if f is continuous, so the continuity part is super important, so I'll underline it, from a to b, then for some constant c, where c is between a and b, there has to exist some output for the function that is equal to the average value of the function on that interval. So this is the mean value theorem for definite integrals. So you can see the definite integral in this theorem, but it's average value, so average and mean. Going back to early stats lessons. So the average value should be accounted for some constant on the interval. So the output for some constant should equal the average value. That's your mean value theorem for definite integrals. Now, there's this really cool connection between area and slope that results from average value and what we learned about the fundamental theorem of calculus. So let's do the area slope connection. So we've spent half the year on rates of change or derivatives, the slopes of tangent lines at various points. We're now introducing or getting into the thick of things related to integrals or area between the curve and the x-axis. So how are these two geometric concepts connected for calculus? We know that the average value is computed by taking the integral of the function and then dividing by the length of the interval. From the fundamental theorem of calculus, part 2, we know that to compute the integral, we have to take the antiderivative at the upper bound, subtract the antiderivative of the lower bound. So these two things are equivalent. So make a note, this is FTC part 2. Okay, so what's going on here? We know that integration computes area. And then look at this formula that we have on the right here. That looks like delta capital F, delta length of the interval in a sense, right? Change in output over change in input. This is the slope from A to B for the antiderivative of F. So this is the average rate of change of f of x from A to B. And we know average rate of change is slope. Specifically of the secant line that connects those 2 points. So we have a connection between slope and area, all coming from our derivation of average value and what we know about the fundamental theorem of calculus part 2 and how we evaluate integrals using antiderivatives. So what we can understand from this relationship is that the average value of a function is equal to the average rate of change of its antiderivative. So average value, we have a formula for it, but we can also interpret it as equal to the average rate, actually let me add in of f of x, is equal to average rate of change for its antiderivative. So pretty cool connection there between area and slope, which seem unrelated at the start, but we now have a connection between differential and integral calculus. So that will conclude the video for average value, mean value theorem, and the area slope connection.